Hello, ladies and gentlemen. So we have a special episode today. Hopefully it will be illuminating for you all.
Yes.
So Eric Weinstein fans out there, shout out to you guys. We're Weinsteins ourselves, or at least I am.
Yes.
But I guess first, guys.
I'm just along for the ride.
Yeah.
So yeah, make sure to like, comment, share, subscribe.
Yep.
If you haven't already. And
check out the web pages, Eigenbros.com, Eigenbros on Instagram, Eigenbros on Twitter, Eigenbros2 on TikTok. And then, of course, thank you guys, patrons. We love you guys. Thank you so much. And you too can become a patron. Support your boys. If you like our content, you guys can get an extra 30-minute podcast on our Patreon. And it's just patreon.com/Eigenbros. So go check that out if you guys want to join and help us out.
Mm-hmm. So let's jump right into it.
Yeah.
So Eric, for those of you not in the know, Eric Weinstein.
I guess technically it's Weinstein.
Weinstein.
He says Weinstein, so we'll call him Weinstein.
He PhD at Harvard for mathematical physics.
Mm-hmm.
Has since become a public intellectual in the physics community, I guess. Right?
Yeah, he claims to be the most followed mathematician online.
Yeah.
Which I could definitely see being true.
Yeah.
Because it's just by the sheer number of times he's been on Joe Rogan, all of this, the Portal podcast, all the exposure he's had with media. Yeah. Mm-hmm. So he's a pretty popular nerd.
Yeah, he's a pretty popular dude as far as like mathematical physics is concerned.
Yeah.
I think well, anyway, I guess I was going to say that his work is mainly in the framework of mathematical physics, although he doesn't call himself a physicist.
Yeah.
He says that he's only ever
makes
taken...
it very clear that he is not a physicist and he's only an imposter.
He said he's only taken 2 classes of physics his entire life.
Yep.
So he's coming at it in... I guess like that's kind of hard to do if you're only taking 2 classes of physics, but
but he's got a little cheat code because he's taken a whole PhD of mathematics, which is basically the entire underlying of physics, right?
Right.
If you can translate all the real concepts into the generalized math concepts, then you're not that far behind.
Right.
Yeah. And clearly, we're the ones behind on this because if you guys have checked out, I guess we're doing this episode because Eric came out with his first draft of the geometric unity paper on April 1st. And he basically tried to outline a good little summary or a first pass, I guess, of what his actual theory is. So he claims it to be a theory of everything or potential theory of everything that explains basically, or at least it tries to tie together, general relativity with quantum mechanics as well as, all the other frameworks of physics like electricity and magnetism and, of course, classical mechanics. Well, I guess it's all kind of tied. But, so he's basically trying to do a first attempt here. And we're going to try to actually give an explanation of what's actually happening here. So I guess let's start one. So... did you get a chance to actually read any of the paper?
I skimmed it.
Yeah.
But most of it is jargon to me.
Yeah. It's pretty damn lengthy and in-depth. And you guys can actually go get the paper.
69 pages.
Yeah. I was wondering if he did that as a meme or if his people did that as a meme.
I think so. Ironically.
Papa Flammy's constant.
Yeah. It's ironically 69 pages. And it's very lengthy and kind of written in Eric's... I would say verbose approach.
Yeah,
like a little bit flowery.
He does a lot of talking.
Yeah,
but he also does a good bit of equations too.
Yeah, so. He does. But I'm saying like a little bit. I don't know. There's we'll get into it.
It's a goodish balance.
Yeah.
Because actually, I actually prefer less equations for this, so I can actually talk about it in a podcast.
Yeah.
Because some of the math stuff is so beyond, especially me and Juan.
Yeah.
Because the prerequisites for this are we're not theoretical we're not mathematicians either, right?
Yeah,
so, and of course, if we were theoretical physicists, maybe we'd be more equipped
for sure,
especially in the realm of particle physics. But you need group theory, and you also need like understanding topology. As well as it would help if you knew Yang-Mills theory, quantum field theory. If you know these things, then you're better set to actually understand what he's talking about. Otherwise, it's going to be kind of a jump, and we don't know any of those things. I mean, you took one course on
surface level.
But you took one on quantum many-body physics.
Which has some QFT concepts, but it's really just literally applied. Like, it's not.
It's not going to help you that much.
You don't know the theory. Like, you don't know the theory like that. You know the theory applied to solid-state physics.
Right.
Pretty much.
So this one, if you really know about symmetries and groups and things, you're going to be much better off. Anyway.
Yeah. So with that, I guess, like, the whole goal of this is to kind of give everybody the language, right, to understand a little bit of the paper. And try to just
get people an understandable take from this. I was actually able to build somewhat of an understanding here. Took me many, many days of research. I think I have something, but we'll try to step through what I've garnered from this.
Yeah, so later on we'll get into the takes of what we think, but for now let's try to build the foundation here.
Yeah, so first I wanted to start off what do you got highlighted here so far?
So this is you have the water fiber bundles.
Yeah, so fiber bundles, I have a nice little lecture by Alex Flerney that I found that was actually really a nice lecture because he even creates the same structure that Eric creates in his theory, the fiber bundle structure, which is a cylinder. And I was like, oh, shit. But I realized that was a really common structure that you use in fiber bundle theory. But it's a really nice video I would recommend. And, of course, we'll put this in the podcast. So if you're listening right now, hopefully that will be understandable. But this podcast might be better suited if you actually went to the YouTube and watched the video.
Gotcha, yeah. So our fiber bundles, for the record, I think they're like the same dietary fiber bundles that you get whenever you
for your intestines.
Yeah.
So let me explain why I even put this. So the fiber bundle is a mathematical concept in topology. That's really important for Eric's theory. So I guess to start off with, Eric uses this fiber bundle structure to actually flesh out an important part of his theory. So I wanted to put this math first. To kind of give you an understanding of what the fiber bundle actually is.
Yeah.
And I guess maybe even to start with that, maybe I should go even simpler and tell you how his theory starts.
Yeah.
So basically what Eric is trying to do is he's trying to create a structure that has very minimal properties. So he's trying to create, so he starts with what he calls a four-dimensional manifold, which he dubs the base space. This would be the base space in a fiber bundle or in a fiber space. So if you just imagine like literally a four-dimensional space, of course you can't really imagine a four-dimensional space, but
3 dimensions, spatial dimensions, and
still 4 spatial dimensions or 4. I don't even know if it's spatial dimensions. Let's just call it 4 dimensions and keep it like very detached from reality.
Okay.
But I guess he does call it a space-time, so maybe we can still say it is a space-time.
Yeah.
But he calls it a proto-space-time.
Okay.
And proto means a primitive, and I guess he calls it a proto-space-time because it doesn't have a metric on it.
Yeah.
So you know what a metric is,
yes,
Juan.
I do, yeah.
It's got to do, so for the audience, you might have seen Eric's videos where he talks about rulers and protractors all the time. He's actually referencing a metric or talking about metrics, and metrics have to do with like measuring space. And really, it's not that fancy. If you just imagine this, I try to think of an analogy for it. You know how water moves in a straight line always, right? Water will always move in a straight line as long as you let it go. If you want water to turn, you're shaping the space around it. So like, let's say if you're in a stream, right? The water is going to move with whatever the topology of the land is, right?
Yeah.
Then the water will curve. So basically, when you're using metrics in a space, you're able to curve the space to where your object, if it's the water, your object is always moving in a straight line, but it looks like it's curving, but it's really just curving with the space. Is that a good analogy? You think?
Yeah.
Okay.
And I mean, like, topology is often like thrown around in physics, and even I got in trouble using this phrase in my defense, in my thesis defense, because I kind of it's kind of become, it can be abused.
Yeah. And these things can be like reserved words in certain
in context.
certain contexts. So you have to be careful with your language, right?
Yeah. So topology in mathematical circles, I would say, strictly speaking, it's more you're talking about a surface. Like you're talking about something that's at least two-dimensional, something that has a shape.
Well, it's a geometry.
It's a geometry.
Usually the surface is a manifold.
Yeah. And that they have names that are sort of like I guess like surface would be manifold. Like there's synonymous things that are used, I guess, in our language colloquially, right?
Right.
Yeah.
Like a surface would be so like for us we think of they call like a sphere. So you have like a general categorization for like a sphere. Mm-hmm. So we know of a sphere, right? It's a 3-dimensional ball.
Yeah.
They might call that a 2-sphere. Yeah. Because the 2-dimensionality has to do with if you zoomed in on the surface of a sphere, it looks like a 2-dimensional plane.
Yeah.
So they call a regular sphere a 2-sphere.
Yeah, because it's literally just a sheet.
Right. But it's just a different language than a physicist would be used to.
Yeah.
Maybe unless you're a theoretical, maybe. But then they call like a circle a 1-sphere. Because it's got if you look at a circle, you can walk on it in 1 dimension. Like it only takes you one angle to be able to quantify any point on that circle.
It's a degree of freedom, essentially.
Right, right. So they call that a 1-sphere. They call a regular sphere in 3 dimensions 2 spheres. So it's like, and that's the manifold terminology. So there's different terminologies that we had to learn for just to understand.
Yeah. And it's that kind of terminology makes its way into physics too, because you get a lot of theoretical physics that comes in and tries to simplify a lot of the stuff that we know, right?
Right.
Yeah.
And like the symmetries make things easier and whatnot.
Exactly. So
But anyway, we've said a lot, so let's actually show what the fiber bundle is.
So fiber bundles, here we go.
In order to even begin to be able to make the statement, I have to introduce you to some math tech called fiber bundles. And fiber bundles they sort of start off seeming like this sort of really cute way to formally treat some interesting little spaces, and we'll talk about those simple examples. But they actually end up being incredibly important and very powerful mathematical tools that get applied a lot in physics, whether you realize it or not. So I'm going to kind of do this in a somewhat formal way to start, and then we'll kind of see the details in the course of an example. So consider, and I'm going to lean heavily on language that we've been developing in GR, but if anybody has a question about something I say, words they don't understand, just let me know. So consider 3 differentiable manifolds. And that word manifold is a loaded word. E, M, and F. Where this E is something I'm going to call the bundle space. This M is what is going to be called the base space, and this F is what is going to be called the fiber space. And what we have in mind is just sort of a working picture of a fiber bundle is that you have this base space M, which can certainly be more than 1-dimensional. It could be, 5, 6-dimensional. But we'll just call that M, and remember, it is itself, by itself, a manifold. And then at each point on the base space, we have attached a copy of the fiber space, which I'll usually just draw as something like that. Again, the fiber space doesn't have to be 1-dimensional. Obviously, drawing these things where these are multi-dimensional is hard. But of importance is that there's a copy of the fiber space at each and every point of the base. Obviously, that's a dense thing. I can't draw it because it'd fill out the board. But that's roughly the picture. And then this just continues. And then the totality of this whole thing is the space E. Okay? So just as a simple example.
So he just built that out basically showing the basic structure of basically Eric's theory as well. Mm-hmm. So that was a very simplified version of what Eric did. So he has the base space M, which he labels. In Eric's theory, that would be X4. So that would be the 4-dimensional manifold base space or proto-space-time.
Yeah.
Then the fiber bundles themselves, F that he labels them, those would be part of the 10-dimensional, I believe, the 10-dimensional part where you have the protractors and rulers. Mm-hmm. So the fiber bundle itself holds the metrics in Eric's theory. And then E, the entire space would just be the combination of the base space along with the fiber bundles. So he has a nice, really simplified version of what Eric's theory kind of looks like. That's a simpler one because his base space is in 1 dimension, whereas Eric's base space is in 4, and then his fiber bundles are in a 10-dimensional space.
Yeah.
I believe. The fiber bundle part I'm a little bit unsure about if it's 10 dimensions, but I do know his base space is in 4 dimensions. And then the theory in total has 14 dimensions.
Yeah, and dimensions often, I mean, from the context of physics, is like the amount of information you can pack, right?
Yeah, it's just like, Eric actually mentions this one time when he's talking with his brother in his sit down with Brett, where he says, like, we're a little bit, like, mathematicians use dimensions in a more, and physicists, we use it in a more, like, people always think of as dimensions as spatial all the time, right? Which is not always the case in math or physics. It's like Eric uses the tongue analogy where you can have salty, sweet, and sour, and those would be 3 dimensions of the tongue.
Yeah.
So if you're talking about a tongue, then you can use those as 3 dimensions. So the thing is, we're just thinking of it in terms of like abstract models.
Yeah.
And then they're the dimensions.
And this is a good example too. Like your tongue is like a manifold, right? And you like have different. It's like a surface, right, where your tongue receptors can kind of be like.
Yeah, but it's a little bit different because the salt, sweet, and sour are independent of the manifold of the tongue, right? Because it doesn't really matter. It doesn't really matter what position on the tongue you're in. I don't think. I think that's like one of those what is it called? Not old wives' tales.
But you tune into that. But your tongue tunes into that information essentially.
Yeah, but I think it tunes it in everywhere on the tongue. So if you want to look,
I don't think so. I think
it does. I think
because your bitterness, all these things, all these different things, I think are more.
No, because if you taste bitterness, right, you taste it everywhere on your tongue. It's like I think I know what chart you're thinking of.
Yeah.
I think that's a it's like one of those things where you're like I use only 10% of my brain.
No, that's not
what
what
it is. I think it is. Okay, that's not what you're saying?
That's not what I'm saying.
Oh, okay.
I'm saying the brain, I think the brain maps. I don't know if every cell matches every sort of information like that to the tongue like that. Anyway, I'm just trying to draw an analogy, but you're saying I'm trying to expand on the analogy, but Eric's analogy about the tongue is more just, hey, this is the tongue. That's the information it's able to get.
Yeah.
You have, your tongue is a structure that's, well, I was going to say your tongue is a structure that's 2-dimensional, but.
Yeah, but anyway. Try not to think so much of the tongue structure. Yeah.
But I mean, like.
It's really independent of the tongue.
Yeah.
So Eric is basically just trying, and this is another thing people may not understand. They're like, how does Eric come up with this fucking crazy model, right? It's like you have to remember that with physics and math and things, like sometimes you're just coming up with an abstract model that you might not necessarily think it's going to represent reality completely, but you're trying to find a model that encompasses all the properties that you know of reality. And then you utilize the mathematics that you've garnered over, centuries to see if you can somehow create a mathematical structure that also matches to reality. And then if that model matches to reality very well, or at least pretty well, then you might glean information that actually does correspond with reality. And then you can see like, oh, this is actually the fundamental structure of reality.
Right.
So it kind of seems a little bit like way out there when you're looking at it from the outside. You're like, how does he even come up with this? And it's really just all the math accumulated over centuries and the patterns that we've noticed from nature and certain mathematical concepts that you take as a rule book, and then you manipulate those different kinds of concepts together, throw different things together, and see if it actually formulates a model that corresponds to what reality actually produces.
Yeah, like geometry itself, it's gone through multiple sort of rigorous, how would you say?
Like reformulations or new formulations?
Yeah, because we had differential geometry. It gave us the whole expansion of relativity. You know what I mean? Like the math was developed before the physics really
existed at all, right? Because Einstein literally was like, I just need some math to make because he came up with the brilliant concept of GR, right? His, what do you call it, like his most happiest thought or something?
Yeah.
where he imagined the guy falling in an elevator being equivalent to, non-inertial reference frames.
Yeah.
And then the rest was history, as they say. So then he was like, I just need to find mathematics that deals with curvature of space.
Yeah.
And then that was differential geometry. And then he fit it onto an abstract model of space-time, making it as a manifold, basically.
Yeah, and you needed manifolds, yeah.
It's like why you always see that sci-fi thing where they have the sheet and then the planet on the sheet dipping in there. That's because of Einstein's whole space-time manifold, basically. And they model, it's like you kind of model, or you can kind of get away with a visual model of the universe as this two-dimensional sheet, even though it's, at least we know it's 3 dimensions space and 1 dimension time. But it still can be it can be seen in the same way, where you have curvature of space equaling gravity, and the more massive something is, then the more space curves. And then if it's super, super massive, it eventually tears space, and then you have black holes and things. So it's like an abstract model that can be fit onto our universe. It may not necessarily translate 100% to how you see things, but the mathematics works in such a way where it yields really, really good results, right?
Yeah.
Like we can actually calculate the metrics for black holes. We can actually calculate the metrics for certain different things in space time. So the analogy is very powerful, and this is kind of the same kind of thing Eric is trying to do here.
Yeah, it's like a professor of ours saying like physics is math with boundary conditions.
Yeah.
Right.
Right.
Yeah.
So mathematicians are well served and well equipped to do physics, but they just need to bring it down to reality.
Yeah. So, second on the list, I don't know if you want to keep showing what's going on here.
I think that's pretty solid.
But you also tried to give like a quick little video on what is a manifold.
Yeah, I liked this one because they just have a little bit more explanation on the manifold, so it still has to do with fiber bundles. It's pretty reminiscent of the first video we watched, but he also kind of shows the cylindrical version of the fiber bundle structure, which is the same one that Eric has essentially. Eric's is a little bit modified in some sense, like he has no ring around 0 for purposes of the math, but it's essentially a very good representation of what Eric, a very close version of what Eric's is as well.
Yeah,
in a simplified way.
So here we go. We'll go ahead and start.
In this lecture, we are going to talk finally about fiber bundles. Very important concept that sort of bridges the gap, or bridges the span between elementary general relativity and intermediate general relativity. We've learned about differentiable manifolds, and that is what it takes to create fiber bundles. And there's a lot of way of approaching how to understand fiber bundles.
I'm a little bit worried because I don't know if I'll be able to speed up the video in my video editing.
We know the speed, 1.25.
Okay.
And the typical way is to, or atypical way is to just sort of present the hardcore definition of what it is and then start showing examples. And the alternative way is to sort of work with an intuition of what it could be and then try to get to a hardcore definition. I think I'll take the second way because there is such a nice canonical example of a fiber bundle that illustrates so much about what it is that it's really hard to resist talking about it. And that is the cylinder. So I'm going to present a cylinder, and I'm going to make a unique a special mathematical construction for a cylinder, and slowly we'll generate and understand what a concept of a fiber bundle is from that. So beginning with this idea, let's take a look at a cylinder. Now this is intended to be an infinite cylinder, so it should go up forever and down forever. And
pause for a second.
So
the up and down forever in Eric's version, it really, if you look at his cylinder there, there's a cutout and there's a circle in the center.
Yes.
That would be again Eric's proto space time in X4, and then positive would be spatial dimensions, and then negative would be all time dimensions in Eric's theory.
Interesting.
Yeah. I don't really understand why that is, but Eric makes a distinction between negative and positive, specifically being a separation between space and time.
Okay. That's interesting.
Yeah, I don't know why, though. And it does extend infinitely as well.
Okay.
One particular circle, which is a cross-section of the cylinder. The cylinder is hollow, by the way. This is a hollow cylinder. So I'm going to just take out one particular circle in the cylinder, and I'm going to call that circle S1. And the reason I use S1 is...
So S1 would be X4 in Eric's theory. He's saying S1. S1 stands for, like we were saying before, a one sphere.
Yeah.
So it's just a circle. So his is a one-dimensional circle, just kind of like in the previous video with Alex Flerney.
is the class of all the spheres is always accompanied by dimensions. So a one-dimensional sphere is S1. Two-dimensional sphere, which would be the surface of a ball, is S2. S3 would be the three-dimensional surface of a hypersphere, et cetera, et cetera. So S1 is just a circle.
So Eric's is X4, four-dimensional.
So with S1 in place, then every point on the sphere, or on the cylinder, and I'll make a point, say, this point here, that point there can be understood with its own, in a coordinate system, right? The surface of the sphere is, in fact, a differentiable manifold. So we can imagine a coordinate system, and the easiest one to imagine is associating that point with a point of the circle, a point of this circle, and some sort of height above the circle. And if we take the height at the circle as, say, 0, then this might be positive height this way and negative height that way. So every point on the sphere will have some member of S1. So I'll say it'll be two coordinates, A and B, where A is an element of S1 and B is an element of the real numbers. And so I can create this ordered pair on the surface of a cylinder, identifying every point on the surface of a cylinder. The coordinate in A in S1, it just has to be a number, for example, between 0 and 2 pi. Well, actually, including 0, it's 2 pi. What am I doing? A number between 0 and, say, 2 pi. Anywhere in that range could be a number for A, but in fact, it could be any number. It could also just be any real number, as long as we understand and identify all values of 2 and pi, where n is an integer. Right? If we create that identification.
I love mathematicians and how they just get caught up in defining things. He's like, real numbers, and we put this on. Actually, yeah, they're part of the same set. He's just like getting caught up in the details. I'm like, okay,
right,
dude.
so rigorous.
Okay, we'll keep going.
Oh, you jumped ahead. Yeah. So I guess I can kind of pause there for a second.
Yeah.
So he basically said A is a point that quantifies some point, or it quantifies some point on S1. In this case, it'd be X4 for Eric. And then that A would tell you any point within the proto-space-time, and then B would tell you a point along the fiber. So the fibers actually extend infinitely, and they create the cylinder. Mm-hmm. So if you imagine, let's think of the one-dimensional cases with XL, XYLY, XL, XYLY.
This dude's
video.
channel, yeah.
That's his channel name is XYLY, XYLYX. So shout out to him, but Jesus, man, get a new channel name. But so if we use his image, which is actually a really good analogy or analog to Eric's pretty much, because Eric uses the same kind of analog. His point B would quantify a point along the fiber itself. Mm-hmm. And that's why he says it's contained within the real numbers, because it can be any number on that whole tube.
Yeah. And
the tube is generated by having an infinite number of fibers that extend out of that proto-space-time, or in this case, the one sphere.
Yeah. Interesting.
Okay.
Let's keep going.
Mm-hmm.
And he uses a point P to quantify that point.
Object about that basically touches on the notion of quotient spaces. Quotient space. And that's an important subject. We will definitely have to get to that eventually, but not right now. In fact, some of our examples will do it. Maybe I'll do it when we touch on some of our examples. But so I can now create this ordered pair for any point on the cylinder. What's interesting about this is I can break this cylinder down into 3 separate differentiable manifolds. This one, the whole cylinder itself, is already a differentiable manifold. I'll call it E. And I'm going to call the E, and that we're going to learn eventually is called the total space. But as we can see by the way we've constructed this, I also have this S1 involved, right? And I also have this real numbers involved. The S1 I'm going to call the base space, and the R I'm going to call the fiber.
So if you pause that, if we want to translate the terminology from Alex Flerney's video, E is still, again, the same
total space.
Same total space. S1 would be, he's saying S1 is a specific one sphere for this space, whereas in Alex's video, he made a generic definition as M for the base space.
You can have an n-fold space. Or sorry,
yeah, an n-dimensional space. Yes, and then the real number for the fibers he called F.
Yeah,
So
but here the fiber in this particular example are the real numbers, right?
Well, yeah, each fiber extends the entire real number line, and then you can have an infinite number of those fibers.
Is he arguing that it's taking values? That fiber takes a number of values, but only in the real number value range?
Yeah, but the real number value range is every number except for complex numbers, right?
Yeah.
So yeah, he's saying that along any fiber, you can take a real number, any real number.
Yeah.
So it's an infinite line basically.
Yeah, true.
And then you have an infinite number of those fibers that create the shape of the cylinder around that base space.
True.
All right.
Yeah, let's keep going.
Basically, the idea now is that this total space can somehow be understood as having part of its basic structure two other differentiable manifolds, the base space and the fiber. All three of these are differentiable manifolds. So I have these three differentiable manifolds. But what makes this important is that I can actually, for a given point, I can write down that point in the total space using this ordered pair in the case of the cylinder. And the ordered pair cleanly places every point in the total space as a point that has a specific piece of the base space and a specific location in the base space and a specific location in the fiber. And I can take those two and create this ordered pair of points. So in this particular total space, every point can really be thought of as a member of the base space in a sense and a member of a fiber in a sense. So it's not really a member because it as an ordered pair is just an ordered pair of elements. The point is an element of E. It's not even an element of S1. It is an element of R, but it's not an element of R in general. It's an element of just the R that we can associate with that particular A. And that's what's so important here, is that what I'm really looking at is S1 Cartesian product R. That is the way E is constructed. And by definition, you can see I took the total space. I just took the base space that the point was lying over, and that became the first part of the ordered pair. The second part of the ordered pair became the real number on this line. So that's the definition of what this is. This is defined as the set of all ordered pairs A and B, such that A is an element of S1 and B is an element of R. Right. So
he said a lot of jargon there, but basically he's just showing you that the fiber, the point P on that fiber is constrained to that point P. Yeah. So you label points along the fiber, and those are individual points. In Eric's theory, each of those points that your proto-space-time intersects will give you a different metric. So you can slide the proto-space-time along that fiber bundle, and it will give you an infinite number of different metrics, or he calls them rulers and protractors, to change your space, or to measure your space, I guess.
Yeah.
And the reason he does that is because he says there's issues that that happen. His whole point of doing this is because there's issues that arise for some reason when you invoke a metric on the base on the space-time, the four-dimensional space-time as it is, which is what Einstein does. He basically says that space-time has a metric already. And Eric is trying to get around assigning a metric to the space. So he goes through all this rigmarole because he's trying to make it so the space is just this pure space, and then the fiber bundle stuff does all the legwork in terms of giving the metric to the space.
I see.
Okay.
Sounds tough.
Yeah, it's definitely tough. It's all really math tricks and working around math to try to get this. So it's a really abstract picture. So if you don't really understand this in any kind of what's it called, internalized way,
yeah,
I don't either, and you're not going to, because it's all math basically, and it's trying to relate an abstract concept. It's trying to explain an abstract concept to how our real life works. But it's just a model. Just think of it as a model. It's like if you imagine trying to make a video game character jump in a game. It's like you can code in physics, yeah, or you can just tell the character to move up 10 pixels and move down 10 pixels. The models do the same thing, but it's like maybe one might be more real than the other, let's say.
Gotcha. Okay.
Anyway. I think that's enough of that video.
Okay. Yeah, so then we also have another video. This one's Theories of Everything.
So this is the, I want to say Brian Keating's. Is it Brian Keating's podcast?
No.
Oh, it's spaced. No, it is. It is. Or is his channel? I don't know if.
It has Eric, Sabine Hossenfelder, and Elise Smolin.
Well, Elise Smolin didn't show up, so no Elise Smolin. But it's also got the space-time dude. What's his name? Like Mark?
Space-time dude?
He looks like normal Peter Dinklage.
Oh, shout out to him. He's cool.
Yeah, he's cool.
He's in this?
Yeah, he's one of the moderators.
Oh, cool. Yeah.
And I think he probably helped bring it together because it's a space-time podcast.
Oh, true.
Crossed
Yeah.
with Into the Impossible.
Yeah. Shout out to him. I love it. I love the videos. I love what you're doing with what's that channel?
PBS Spacetime.
PBS Spacetime.
Yeah.
Thank you. Yeah.
Yeah, so Eric in this one is basically giving, this is like one of his better, I think, explanations of what his actual model is.
Yeah.
And he even has a nice little visual aid of toilet paper rolls.
Good, because I know Eric, and there's a camp of these physicist dudes that are anti-reductionists, and I don't like this.
What do you mean? Can you explain?
Anti-reductionism is more like you don't want to talk down to people, you want to give them the information as it is.
Yeah.
But I'm like, you're losing everybody.
Yeah, sometimes we need to get talked down too.
You're losing, like, it's like a PhD, and this happens with PhDs a lot, because when you give a talk,
yeah,
a lot of professors they don't want to talk down, but this is like, dude, only 10 people in the world know exactly what you're talking about.
Yeah.
Like, probably even, you know what I'm saying?
Yeah, maybe even less, because even those people are scratching their heads, huh?
So it's like academia has a lot of these people that they're kind of trained to be anti-reductionist, but I'm like, let's scale it back a little.
I don't even think it's them being trained. I think it's just so hard to try to distill these concepts in an understandable way.
Whose fault is it?
Well, it's really the explainer at the end of the day, right?
Yeah. I know. I'm kidding. But
it's tough, man. It's tough.
Yeah, I know.
Because Eric, I would consider as like a top tier explainer, and even he has trouble doing this.
But
it's just such an abstract model.
Yeah, but I appreciate any time any analogies are brought in, any kind of analogs. And I know there are people I've heard physicists say that are anti-analogies, like they don't want to use them. They just want to tell it like it is. And okay, but you're only talking to yourself then, because no one else understands what you're saying.
Right.
So anyway, with that being said, let's go ahead and see what we got here.
All right.
So first of all, Sabina, I thought you were going to say something like this. This is preposterous. By the way, I think the world of Sabina, her integrity and her curmudgeonly nature have been a huge boon to physics. So keep doing what you're doing, and there's no one I'd rather fight with. Given that the gloves are off, Sabina, that's not true. Look, assume that you had a space-time manifold, right? And normally we need four dimensions for that. Before you have a metric, here's a one-dimensional manifold in the form of a circle, okay? Now, it happens that you have to create in geometric unity an ambient space, which would be a fiber bundle, okay? That would look like, in the case of a circle, a disconnected object, which we will call Y, call the hair tie X, which is that band around the core. And this is Y, which is the space of metrics. These would be time-like, these would be space-like metrics, right?
So pause.
So the idea is...
So that pretty much goes back to what we were saying. Why is my audio coming? Oh, okay. Yeah, so that's that goes back to what we were talking about with... Basically, Eric has the hairband representing the X4 proto space-time. The toilet paper rolls are the fiber bundles, which he calls Y. So in this, and then that, in the analogies from before with the fiber bundles, that would be F in Alex Flournoy's analogy, and then it would be M for the hairband. And then he said he makes them two distinct paper rolls because he needs to cut out a center where there's a zero, where there's effects with zero or something. So zero is involved, so it's at the center. At the
torsion, it's like, is it torsion?
Yeah, it has to do with the torsion part. So you read that part in the paper, yeah.
Yeah, I just know what torsion is. It's like
Okay.
it's a like you can also twist the space. It's whatever.
So they can't he can't handle the math there, so they cut it out.
Yeah.
And then then there's only the space time portion, and then the the time portion and the space portion are separate.
Yeah.
All right.
Is that an Einsteinian space-time is a wrapping, if you will, of a hair tie around the core. And the idea is that the physics is taking place both on the hair tie and on the core. All right? And so if the space-time metric is down here, you're going to pull back different information at the bottom of this core than if it were at the top. That's just saying it's a section of the bundle of metrics. That's straight up Einstein, right? What I am saying is that the bundle of metrics, this object Y, has a funny feature, which is that it has a metric on it almost. So I'm going to put a toothpick right now through the core of the roll, representing what I would call the horizontal tangent space, which is not pointed along the tube. If it was pointed along the tube, then the Y structure would have a metric, and then it could have things like electrons and muons and neutrinos and the like. But in fact, it points off. So one of the issues of geometric unity is pushing this horizontal subspace along the tube to be a perpendicular to the vertical subspace. Therefore, the space of metrics that Einstein gave us actually weirdly almost inherits a metric without any choices of a metric on the original space. On that, you define all of your particles, and the 10 dimensions that Einstein gives us of the coupled partial differential equations are the same 10 as the spin 10 unified theory. Okay? So the idea is you have a coincidence. You learned about something involving 10 in the case of Einstein's general relativity. You also have 10 cropping up in grand unified theory. 10 is 2 times 5 for the SU5 theory. If you think about something called the Petit Salam theory, that's usually given as SU4 cross SU2 cross SU2. It should be called spin 6 cross spin 4. 6 plus 4 is 10. 10 is coming up over and over and over again. It's also d squared plus d divided by 2 if d equals 4, right? All of these things give you a structure where there is no internal symmetry groups.
You made an error there.
And that was the huge problem with supersymmetry, is that you never got rid of the double origin story. You had a space-time origin story, and then you had a fiber origin story where out of the blue, or in Yiddish, inmitten drinnen, coming from nowhere, you put SU3 cross SU2 cross U1, which, because you never pulled that out of anything organic and geometric, the idea is that when you did supersymmetry on top of it, by the way, which is not a symmetry, I don't know why we insist on calling it that, you were working on the wrong group. The idea is that where you saw the Lorentz group is where you should use the gauge group. Now, Sabina, what you call the gauge group is actually technically called the structure group. So I'm not talking about the finite dimensional objects that you were talking about before. But you should form the infinite dimensional gauge group. And just as you form the inhomogeneous extension of the Lorentz group, to form the Poincare group, you should form the inhomogeneous extension of the gauge group, which is an infinite dimensional gadget. Do supersymmetry on that, remove the internal symmetries, and generate them by the virtue of the fact that the proto-spacetime, before it inhabits the province of Riemannian or semi-Riemannian geometry, you should look at the bundle of metrics, realize that that almost has a metric on it, therefore it effectively almost has spinors on it. And closing out this little riff on geometric unity, one of the problems that people keep talking about, we can't quantize gravity. You have a bigger problem than that, which is that the electron and the quarks and the neutrinos and all these particles that are matter depend on a particular choice of a metric. They don't exist in the absence of one. So you have, in the case of a photon, you have the C in which the photon is a wave, if you will, and then you have the wave itself. And you can say, well, I don't know where the wave is between observation. If you don't know where the metric is, then you don't know where the ocean is between observations. And the difference between being at the beach and not being exactly sure where the waves are versus being at the beach and not being sure where the Pacific Ocean is an entirely different world of pain. And for whatever reason, the physicists are not particularly bothered by this. So one of the things that geometric unity does is it takes the issue of the fact that the electron bundle the medium in which the electron is a wave doesn't exist between observations of the metric. And it says, we're going to solve that for you by working over the space of all metrics, showing that that has an almost metric coming from the fact that it has a chimeric bundle, which is partially along the space and partially pointing away from the space. Geometric unity tamps that down, and that means that electrons are defined between observations of a gravitational metric, which could be up here or down here, because the entire space of metrics effectively has a metric. So I don't believe...
Let's give us...
Oof, so that was a mouthful. But I think the big takeaway from that was just Eric's structure of his fiber space, basically. And then the chimeric bundle, which he talks about, where that hides or that allows you to utilize those metrics without applying it to the proto-space-time initially.
Yeah.
Because I guess with Eric, what Eric is saying, that there's a flaw with Einstein's theory in the sense that there's a metric already ascribed to space-time right from the get-go. So it's like an extra axiom or assumption that Eric's trying to circumvent. He wants to start with just a space-time structure with no metric, and is using all these fiber bundle things with the chimeric bundle, with a tangent vector or whatever. I forget what it exactly is.
Vector space, essentially.
Yeah, that was a little bit harder for me to understand. But but the takeaway, I guess, is from that is that's how you apply back, or that's how you take the metrics from the fiber bundle and apply them back onto that proto space time, so that you can get around ascribing a metric initially.
There's like a mapping of sorts.
Yeah. So his whole goal is to map, or to start from an X4 proto space time and map all the metric information onto that space without actually assigning it to the space initially. That's the whole point.
Yeah, and we call that in physics, like, it's like a projection, like you project from one space to another.
Yes. So he's finding some fancy ass way to project on a space by invoking 14 dimensions, essentially. But I mean, I can't be mad at him, because I mean, it seems legit to me. The more I read it, I'm like, okay, this actually makes sense to me, at least at some level conceptually. I don't understand the math in any great detail, so of course I cannot enlighten you on the rigor of his mathematics. And there's also some critiques I saw about his Cheab operator specifically, which is a big part of his theory. Tim Wen and a guy that goes by the name Field Theorist sometimes. He's another alias. I think he calls himself Theo something. It's an anagram of Field Theorist. But anyway, they wrote a paper as well that's on Sabina's blog about some problems with Eric's geometric unity, and one of them was the Cheab operator, which is a big part of his theory. The Cheab operator would be a big part mathematically to resolve some of the inconsistencies in his theory. And Eric actually is pretty forward about this in his paper and names some of the problems in his paper. But of course, this podcast is going to be a first pass. I'm sure we'll probably do more in the future, but the math is so extensive, I can't really even comment on the issues with that.
And operators, for those of you that aren't familiar, are just, they're mathematical operations that happen on your space, and they have a certain set of defined
or on an
rules.
object
Or on an
general.
object in general.
So you can imagine it as just like, even like, you change, so even object is a ball, right? And you have a blue operator. If your blue operator acts on your red ball, let's say, then it turns your ball blue. That's what an operator does. It changes something about an object.
Yeah, but I mean, like I'm saying, like in everyday math, though, like an operator. I mean, we know it more intimately whenever we get into calculus, because doing a derivative is a mathematical operation, and that's an operator. It's the derivative.
Yes. It changes your function. It changes an object. Something.
Yeah. So but yeah, that's kind of one critique I've seen. And that's kind of important if you're a mathematician. I guess, like, for him, he's just trying to paint a picture, right? Starting out. So he's having a difficult time, maybe, like trying to describe how the operation
Well, I
might
think
work.
one of the reasons why Eric is so reluctant, because I know we wanted to discuss this about how Eric's taken so long to come out with a paper, and he's really like guarded about how he does it. And I think one reason is probably because his theory is incomplete, and the mathematics behind some of the things like the Sheop operator specifically, maybe one of the other things maybe connection. I don't know for sure, but the Sheop operator, I guess specifically, it's like there's some things that are like really open holes that are big parts of the theory that need to be resolved. And I think Eric's really scared of people throwing away his theory because he talks about dead on arrival theories, where people will propose something and then it will get attacked immediately because it doesn't solve X, Y, and Z.
Yeah.
And then he calls it a dead on arrival theory. And he thinks that we should be careful of that. He even addresses this in the paper where, Schrodinger, famously had the Schrodinger equation, right? And what?
No, I'm just thinking about Schrodinger.
Yeah, Schrodinger
I know where you're going with this.
Schrodinger had the Schrodinger equation, but like spin wasn't taken into account of it.
Yeah.
Even though experimentally we saw spin in the lab, right? And then he also mentioned even Dirac's equation, right? When it had the Dirac C, and he said that there should be protons in the Dirac C, but it was actually the anti-electron.
Yeah.
So there are certain things that he talked about. I think it's a principle of instantiation.
Yeah, he was worried. There's a lot of psychological stuff that goes on with this. I think. As far as like the math goes, if you're somebody who's like outside looking in and just kind of interested in like what the hell is going on in the physics community.
Yeah.
Hopefully this gives you a primer.
This will make you take a 360 and walk away.
By the way, that's a joke. We know what 180 and 360 are. Okay.
It's a yielding meme for those people who are on the old internet.
Yeah, exactly. But it's as far as the content matters is how would you say? I'm losing the phrasing here.
The content of Eric's paper?
Yeah, we hope we provided a sort of primer.
Yeah, I just want people to understand, and like, because Eric's a public intellectual, right? And people see him on Joe Rogan. He's a smart guy, and I'm sure they want to know what he really does. The fucking Tim Dillon rant was hilarious. He's just like, what do the Weinstein brothers do? Like, what have they done? Have they made an appliance or what? And I'm like, trying to give it to people to understand this is what Eric does. He's a researcher. He creates a lot of abstract theoretical frameworks for things. He's a gauge theory guy. So he works with a lot of gauge theory stuff. That's why he went to economics. But of course he's a mathematician and a play physicist. So, once you got the math, you can do a lot of different stuff. So this is what Eric does. He's a mathematician. He plays with models.
By the way, I like how at the end of his paper, he was like, "This is for entertainment purposes only."
Yeah. He called himself an entertainer and a podcast host. I'm like, all right, Eric, calm down. He's really trying to
He's trying to just whoosh, like Matrix his way, like, bro. I mean, okay. Look, Eric, I can tell. There's a lecture he did on his first. I think the first time he ever gave a public lecture on his.
That is the video.
Yeah,
right
a
there.
portal special presentation, geometric unity, a first look.
Yeah.
If you go and watch this video, he goes a lot more into detail of his theory, and it's a lecture, so you'll be able to sit down. And
there's a particular part at the
minutes,
end that I have here.
Okay, in the first 30 minutes, he kind of goes into why he's doing what he's doing.
Yeah,
and it's a whole, basically, lecture. I'm sorry, I'm laughing because I can tell that he's been hurt. The man has been hurt. The man has been down bad, it sounds like. He's been hurt by the institutions. It looks like he had a hard time getting his PhD. Professors didn't like him, it seems like. He looks like he butted heads.
Yeah, they tried to phase him out.
Yeah, and look, we're no strangers to that, Terence.
I never got phased out. I kind of phased myself out.
But we've seen it happen.
I don't think we're important enough to be phased out.
Right,
it's
right.
Like, you'll fail on your own.
Yeah,
it's fine.
But I've seen it happen, and it's definitely it's sad, but there is kind of like the chip on the shoulder aspect of it.
Yeah.
I noticed that
but Eric went a real ballsy route because he had no advisor.
Yeah, I know, but that rubs people.
Yeah,
rubs people the wrong way because it says one of two things. It says you either don't like working with, like you don't like taking criticism, because your advisor's there to criticize your theory,
right? And they're supposed to guide you on the track to like doing proper research. Like Eric was trying to be too much of a
lone wolf,
which doesn't really work at this day and age.
And he commented on this video saying, "I don't believe in this communal bullshit of science." He really said
Did he say that?
I mean, not verbatim,
Okay,
but
I
like
was gonna say.
he said he doesn't believe in the communal aspect of science because he thinks a lot of the science community is very egotistical and all this other stuff, which tells me, I mean, he's been attacked, and he doesn't. He's clutching his theory like pearl clutching. You know? I can tell that it's his like brainchild and that he cares about it a lot. But part of this stuff that we think about, these models that we build, is asking people what they think about it.
Yeah.
Right.
You need to have peer review for these kind of things, and especially collaboration. For Eric to try to come up with this on his own,
and he said he doesn't want collaboration, though.
I think that's why he's trying to do it in this strange roundabout way as well, because he's wants help from people, but also Eric has dyslexic problems, some learning issues. I know he says he's symbolically challenged. I think he's trying a new way so he doesn't get fucked by academia, because he also has a history of it with his family. Like his brother got scooped basically for his whole telomere stuff with Carol Greider, where she took his research idea about mouse telomeres. His wife Pia Mullaney got her stuff kind of co-opted by Juan Maldacena when it comes to gauge theory, and I think maybe some economic stuff. I can't remember exactly. So Eric is kind of he's a little bit guarded when it comes to academia.
Yeah,
maybe a little bit too much so to his detriment.
Yeah,
but that's him, and Eric has a large following, so maybe he can try it a new way. We'll see.
No, yeah, and I get the arguments, because it's like he was saying, the people who get credited are not the people that tried first.
Yeah,
and science, at least.
Right. Sometimes
they are. I agree with you.
Yeah,
but in his experience, he has been he has seen science go more to the people who were successful at launching instead of failure to launch. Like
right.
And it's not like in history where we say like the Wright brothers. We were like, look, these were the first people that tried to do it.
It's not always how it goes.
In science, it's not. In science, it's always like what works.
Yeah.
What worked and what
you can stand on the shoulders of a bunch of bodies, from the people who failed.
Nameless bodies, yeah.
Right.
And that's kind of
that's the guy who gets the credit.
Yeah, and that's kind of
Maxwell writes one addition to an equation, and now it's all his equations.
Do you see that? This is why Eric is pissed. Yeah, and there is, I know, right? Because each of the Maxwell's equations have their own, like, it's Faraday's.
Right, they even got the names: Ampere's law, Faraday's law, Gauss's law. What happened with them? Why is it not their equations?
Yeah, man. I mean, it's true. I mean, it's so true.
People are like, Maxwell's a genius. He unified electrodynamics all on his own.
Yeah, so
no, I'm just jesting.
I
no
know,
hate towards Maxwell at all.
No, I know, but that also infuriates me, because it's like you should give credit where credit is due.
Yeah,
and I get where Eric is coming from. He doesn't want all this to be done in vain. He wants to contribute, but on his own terms. Which I respect, but I think you gotta
put up or shut up.
You gotta put up a lot of the time. You gotta put up or shut up. Yeah.
I mean, he has his first draft out, so
that's good.
That's an improvement.
So I commend you. If you ever want to come on the Eigenbros, Eric, this is.
Bro, he ain't watching this. Actually, Eric has watched our podcast.
I know he
told me he has.
Yeah, I know.
I was like,
Eric, I know you.
Wow.
Eric, I know you care what people think about your theory. I know you care about how people feel. So if you wanted to clarify, this is your platform.
Yeah, we're always here for you, Eric. We love you, Eric. If you are watching this, probably not, but in the off chance,
we'll treat you nicely. We won't hurt you like those academics did.
Yeah. Only love in the Eigenbros.
Yeah, only love in the Eigenbros circle. So, but you had this video. I don't know what.
What's our time? So
I think we're about an hour. Yeah.
An hour.
Do you think we still have time to look at this video? What was the context of this?
Is it exactly an hour?
Yeah.
Oh, I think we can a little bit. We can just listen to it a bit, because Not much. It starts to get a little bit complicated, so I think we can look at it. But this is just the video after Eric gives his lecture. So he actually does a little bit of a a pre-recorded tape after the fact of some of the stuff that I think he was probably working on with this new draft.
Yeah.
And kind of gives you a little bit of an understanding, a little bit of the observerse and things.
Okay.
In Sector 1 of the geometric unity theory, space-time is replaced and recovered by the observerse contemplating itself. And so there are several sectors of GU, and I wanted to go through at least 4 of them. In Einstein's space-time, we have not only 4 degrees of freedom, but also a space-time metric representing rulers and protractors. If we're going to replace that, it's very tricky because it's almost impossible to think about what would be underneath Einstein's theory. Now, there's a huge problem in the spinorial sector, which I don't know why more people don't worry about, which is that spinors aren't defined for representations of the double cover of GL4R, the general linear groups.
So the general linear group GL4R he's talking about just has to do with it's in group theory it's just saying n by n matrices that are invertible, essentially. So nothing too crazy.
Effective spin analog. And as such, if we imagine that we will one day quantize gravity, we will lose our definition not of the electrons, but let's say of the medium in which the electrons operate. That is, there will be no spinorial bundle until we have an observation of a metric. So one thing we can do is to take a manifold XD as the starting point and see if we can create an entire universe from no other data, not even with a metric. So since we don't choose a metric, what we instead do is to work over the space of all possible pointwise metrics. So not quite in the Feynman sense, but in the sense that we will work over a bundle that is of a quite a bit larger dimension. So for example, if X was 4-dimensional, therefore D equals 4, then Y in this case would be D squared, which would be 16, plus 3D, which would be 12, making 28, divided by 2, which would be 14. So in other words, a 4-dimensional a 4-dimensional proto-spacetime, not a spacetime, but a proto-spacetime with no metric, would give rise to a 14-dimensional observerse portion called Y. Now, I believe that in the lecture in Oxford, I called that U. So I'm sorry for the confusion, but of course this shifts around every time I take it out of the garage, and that's one of the problems with working on a theory in solitude for many years. So we have 2 separate spaces, and we have fields on the 2 spaces. Now what I'm going to do is I'm going to refer to fields on the XD space by Hebrew letters. So instead of G mu nu for a metric, I just wrote Gimel Mem Nun. And the idea being that I want to separate Latin and Greek fields on the Y space from the rather rarer field that actually live directly on X. So this is a little bit confusing. One way of thinking about it is to think of the observerse as the stands plus the pitch in a stadium. I think I may have said that in the lecture, but this is what replaces the questions of where and when in the newspaper story that is a fundamental theory. Where and when correspond to space and time, who and what correspond to bosons and fermions, and how and why correspond to equations and the Lagrangian that generates them. So if you think about those 6 quantities, you'll realize that that's really what the content of a fundamental theory is, assuming that it can be quantized properly.
Okay.
Most fields...
So Eric gives a nice little summary there of his theory once again, and shed some light on some new areas, I guess. He refers to the fiber bundle set. So the set of all the fiber bundles coming from the proto-spacetime as the observerse.
Yeah.
And then he makes the analogy of like the Pittston Stadium is what the observerse would be. And then you're looking at the field, or the arena, as Eric likes to call it sometimes, as a proto-spacetime. What that means, I don't know. So we got to figure that out one day. But yeah.
Well, yeah, we'll definitely get some more. I want to get some more people on. We have friends that are mathematical physicists, so it'd be good to get their takes on it. We can definitely sit them down and.
Well, I've got some people also that I would hope to get on. I'm not going to say who they are yet, but I'm hoping I can maybe get them on to talk about GU.
That's good. Yeah. Because, I mean, fleshing out a lot of these concepts would be nice. Like, for me, I'm not a theoretical physicist, but being able to talk about these things to some capacity is nice.
Yeah.
You know what I mean? Like, just having a sort of conversation over coffee kind of thing is good. So if you're someone like me, I hope this podcast was useful. I definitely learned a lot of things. I didn't know what the hell fiber bundles was.
Yeah, I
don't like the name.
Too.
I don't like the categorization.
I was like, who the fuck invented fiber bundles, and why would you?
Why would you decide? Also, why would you
Seems so random.
Why would you name it something so that already has an association with something? Because a lot of naming conventions have a problem, because if you have an association with, if you associate that word with something, it's harder for your brain to.
Well, what is fiber bundle are you associated with?
Well, you have two words that already have their own meaning, fiber and then bundle.
But not in a mathematical context.
Yeah. But I'm saying, like, why not pick a whole different, like, why not pick a different phrase?
I'm not so mad at it.
I am.
Because it actually does correspond with the picture that you would see in your mind, strangely enough.
No,
I'm just like, why would you even name it like this, though?
Because when I think of a fiber bundle, I think about, like, something like a thread.
Yeah, that's good.
Oh, that's good?
Yeah, because it is like a thread.
Oh, okay.
It's just a bundle of threads. So it is intuitive to what you think it is.
Oh, okay.
Yeah.
All right, well, then there you go.
That's why they named it that way.
Okay, good. All right, excellent.
Because you saw the pictures, it literally is like a thread. The thread is just as a number line. And I guess it can be wavy or whatever because it's got all the metrics.
So why has nobody said that?
Well, they showed you pictures of it.
No.
It wasn't enough?
It wasn't enough. They could said it's kind of like a thread.
It goes deep. Yeah.
You could have just said that. I'm like over here thinking.
I guess they call it a fiber instead of a thread. It's a piece of fiber. I don't know, Juan. Thread, fiber, what do you want, man? All this stuff is all abstraction bullshit anyway, so.
I know, but that's kind of my issue. Like, I'm just like, can you give me some concrete, like something to tie it into reality for me, please?
That's what they try to do.
Yeah.
Fiber.
All right.
But I guess I should mention that I think it was the reason that Eric's trying to do this fiber bundle stuff is because the geometry they found a way to make geometry tied to QFT stuff, and like they call a standard model SU3 cross SU2 cross U1, which has to do with the symmetries of standard model.
Yeah.
The geometries that underlie that are the fiber bundle theory with Yang-Mills and whatnot.
Yeah.
The geometry of special relativity has to do with like differential geometry, and Eric's made a point that the two geometries are incompatible. So he's trying to make it so that the geometries will actually fit together at the end of the day, instead of trying to quantize gravity like everybody else is trying to do.
Ham-fisted.
Well,
they're trying
not so much hand-fisted because they just think that quantizing gravity is the only problem. Eric sees it as the geometry is the problem. He's like, they've had their shot trying to quantize gravity. It ain't happened yet. So Ed Witten actually mentioned that you should go back to the geometry and look at that. So Eric's looked at the geometry to see if they could find a way to converge the geometries, because it's two different geometries.
Yeah. Cool.
Makes
All right.
sense?
Yeah, that's
All
good.
Right. I guess that's good enough, right?
That's good, yeah.
All right, guys. So make sure if you like that stuff, like it, like the video, comment, share, subscribe to the channel if you haven't already. Check us out at Eigenbros.com, Eigenbros on Instagram, Eigenbros on Twitter, Eigenbros on 2 on TikTok. And thank you again to the Patreon subscribers. We love you guys. We appreciate you. And if you want to become a Patreon too, just check us out at patreon.com/Eigenbros.
Yeah.
And we will see you guys next time.
Peace.
See ya.